High Roller is a famous roller coaster and was one of the first built at Valley Fair. Before the ride, we were feeling excited to get back on a roller coaster, and Caden was very wet. We expected a rush of adrenaline after the first big drop and more mild thrills following it. We have heard that it's not that scary, but it's still fun. It is marketed as a classic ride that many would call their favorite. After riding it, we could all agree that it was a fun experience and it gave us that stomach-dropping feeling. Like we expected, the most exhilarating part was during the main drop, but it was more of a rush than we remembered. We would describe it as a fun, stereotypical roller coaster that anyone can enjoy. The ride starts moving when the chains pull the cart forward. Once the cart hits the first hill, it latches onto a chain that pulls it up. These are powered by an engine beneath the track that powers the wheels and chain and causes them to spin. After the cart goes down the first hill, it has enough kinetic energy and momentum to carry it through the rest of the coaster. Air compressors clamp down brakes on the cart to slow it down when it reaches the end.
This is an energy bar chart for the high roller. Initially at the peak, all of the energy of the roller coaster is in gravitational potential energy. However, at the bottom, only 25% of the gravitational potential energy was converted to kinetic energy. 75% of it was lost to internal energy, also known as heat. These are the force diagrams at different stages of the high roller's descent. At the top, only normal force and gravitational force are present. At maximum velocity, gravitational force is still pointing straight downwards, force normal is perpendicular to the track, and force friction is parallel to the track. At the bottom, when it's a straight track, there's friction force to the left, and a balanced gravitational force and normal force. Through our very advanced trigonometry, we figured the height of the coaster's peak to be 18.41 meters. This means that the filled coaster cart with a mass of 3,960 kilograms has gravitational potential energy of 714.5 kilojoules. The same cart was measured to have a velocity of 9.56 meters per second at the bottom. This means the kinetic energy was 180.9 kilojoules, meaning that only 25% of the potential energy was converted. 533.6 kilojoules were lost to an internal energy in the descent. This is very inefficient. Energy is from the gears. Acceleration of this coaster is dependent on the coefficient of friction and the slope of the incline. The slope of the incline affects the parallel component of force gravitational. The mass would decrease the gravitational force along with the friction force, so it's a bit indeterminate compared to other factors. A smaller coefficient of friction would reduce the force acting in the opposite direction, allowing the cart to have greater acceleration. We measured the high roller's velocity to be closer to 9.5 meters per second. However, the actual velocity is closer to 22.35 meters per second, making our high roller kinetic energy result a bit more invalid.
The Flying Eagle is a spinning ride where the rider sits in an eagle-shaped cart and flies in a circle. Before the ride, we felt excited because none of us have ever tried this ride before, but besides that, we felt normal. We expected it to be like other swing rides, where you are high up and swinging in a circle. We have not heard anyone talk about this ride before we rode it. It is marketed as a ride mainly for kids who don't want to try scary rides, and after riding the Flying Eagle, Caden said he felt slightly dizzy and sick. It was similar to other swing rides, except you could turn in your cart. Still, it felt very similar. To describe this to someone else, we could compare it to other swing rides. This ride works by an engine that turns a pole that all the carts are connected to via chain. This increases the tension in the chains that the carts are on and makes them go up and around the axis.
Oh! For the Flying Eagles, the angle that the rope makes with respect to the ground was 45 degrees, and the centripetal acceleration was 14.2 meters per second squared. This was because the tangential velocity that we found was 7.62 meters per second, and the radius of the actual rope holding the swing was 4 meters. The radius was 4 meters because we were using the horizontal component of the length of the rope, which was different from the radius of the entire circle part of the ride because of the design of the ride. We found that the period for one full rotation was 6.7 seconds. The diameter of the cart's circular path was 25.5 meters. This means that the cart's displacement in half of the period was 25.5 meters. We know this because displacement over time equals velocity. For the kinetic energy, we were able to plug in the numbers that we found in our data and do 0.5 times 7.62 meters per second squared times the mass of each of the swings, which was 1,349 kilograms, which equals a total of 39.2 kilojoules per swing. In the graph shown, you can see that the acceleration for the Flying Eagle's ride is changing in the beginning, while throughout the middle of the ride it is mainly constant. In the end, there are peaks shown because the deceleration is at a changing rate. In the Flying Eagle's ride, as the ride is moving, there is a net force on the swing, causing the swing to spin in circles. This is evident from the force tension being inwards, while the force gravitational is straight downwards. On the other hand, while the ride is not moving, the force gravitational is pointing straight down, while in the equal and opposite direction there is a force normal pointing straight up.